All right.
Take it away.
I guess it's time. All right. Hi, everybody. For those of you who don't know me, my name is Zach. I'm a master's student in the department here. And this talk is about some work I did with Eric Talvady and Mike Bowling. Can't tell from the title, it's about using Dyna in high-dimensional state spaces. It's a bit of a long title, but it's a pretty good summary of everything I'm going to talk about. And I feel that this work is pretty relevant considering Rich's talk last Monday about planning being the next big step for AI. So for this talk, we're going to use the arcade learning environment as our problem with the high-dimensional state space. So the ALE is a test bed for RL agents. And in the ALE, agents learn to play games from the Atari 2600 system using raw images as input. The ALE is considered an excellent platform for evaluating AI agents for three main reasons. The games are quite varied in their mechanics and gameplay, so that means that agents need general competence to be able to do really well. The games are interesting and challenging for humans. And three, the games are free from experimenter bias. So since they're originally developed for games for people to play and not as a evaluation platform, there's no bias built into them. So most of the successful approaches for the ALE can be considered model-free in that they don't use a predictive model of the environment's dynamics. So they learn a value function or policy directly from real experience. So alternatively, model-based methods make use of an explicit environment model for planning. So planning in this sense is any process that takes a model and uses it to produce or improve a policy. So usually model-based methods are more complex than model-free methods, but they can often make better use of limited experience and learn a good policy with fewer environmental interactions. So a prime example of a model-based architecture is Dyna. So this is a figure from Sutton and Bartow. So you have the normal RL thing where the environment is providing real experience for the agent, and that agent uses the real experience to update a policy or value function directly. But in addition to this, the direct RL part, it makes use of a model, which is usually learned online, to generate simulated experience, which is then used to update the policy and value function and the experience is used in the same way as the real experience. So an example of an instantiation of this is the Dyna-Q algorithm, which combines tabular Q learning with Dyna. So the first algorithm that might come to mind when you think about the ALE is DQN. DQN is a model-free deep RL method that's based on Q learning. It has lots of details and tricks that make it work, but the only one we really need to know about right now is that it uses experience replay. So for experience replay, the agent is still interacting with the environment. So the environment still produces state information, which is available to the agent. But the agent doesn't use that information right away. Instead, it puts it into an experience replay buffer. So then later, at some frequency of interactions with the environment or steps, the algorithm selects a batch of states from the replay buffer and then uses them to update the value function. So to extend DQN to the Dyna architecture, after every real step taken by the agent, we can use a model to generate simulated experience and then also put that experience in the replay buffer alongside the real experience. So right now, we're assuming that we have access to a model of the environment and that we're not learning that online. And start states for planning, they have to come from somewhere. So what we're going to do is we're going to keep track of a buffer of the agent's recent real experience and then draw sample start states from there to do planning. So in addition to the real environment that's generating states, we have a model that's also generating simulated states. And then both real and simulated states get put into the experience replay buffer. Then when we update the value function, the batches will contain a mix of real and simulated experience. And then this continues to happen at the same frequency, but now we count steps taken with the model as well. So if the training was happening every 4 real steps before, now we count maybe it happens every one real step and then 3 simulated steps. Is everyone following so far? All right. So to evaluate Dyna-DQN, we ran it on several games from the ALE, and we used a perfect model, which was just a copy of the emulator, to explore like the idealized performance of this algorithm. So for every real step in the environment, Dyna-DQN did 100 planning steps. So it sampled 100 states from the buffer and then did one step, simulated one step. So we trained for 100,000 emulator frames, which is equivalent to 10 million combined frames, because the emulator or the Dyna-DQN has 100 times more experience than real frames. And then after training, we record the mean score in 100 evaluation episodes, and we average over 10 runs. So we also ran several baselines for comparison. The first one is DQN just trained for 100,000 frames. This allows us to compare DQN and Dyna-DQN with an equivalent amount of real experience. So we would hope that Dyna-DQN outperforms the first baseline. And then the next baseline is DQN extra updates. So this is DQN trained for 100,000 real frames, but with the same number of updates to the value function as Dyna-DQN. So for each time DQN would normally perform a single training step, DQN extra updates does 100 training steps. This way, DQN extra updates is like Dyna-DQN, but it uses experience. So Dyna-DQN uses experience gathered from the environment, while so DQN extra updates uses only the experience that it has already collected, whereas Dyna-DQN generates more experience. So this allows us to evaluate the advantage of using the model to generate new experience compared to just doing more updates with the experience we've already collected. And then the third baseline is DQN trained for 10 million frames. This allows us to compare DQN and Dyna-DQN with this equivalent amount of total experience. So we might hope that the experience generated with a perfect model would allow Dyna-DQN to perform like similar to this third baseline. So here are the results. So Dyna-DQN is the bright green bar. And we can see that in most cases, it doesn't do much better than the red bar, which is just doing extra updates with the experience you've already collected. And everywhere except for Seaquest, which is kind of an anomaly, it doesn't do nearly as well as DQN 10 million. So that's not great.
What did you do about parameters?
What do you mean?
Well, you should feel an obligation to tell me how you set the parameters to make this a fair comparison.
All the DQN parameters are the same in each case.
So you just kept whatever they.
Yeah. Well, what was it?
Them.
No. So they weren't. So we didn't tune any of the hyperparameters for performance. We just used what was originally published with the DQN algorithm, and then added on this planning module to it.
So the results could be totally different at different parameter values.
Yes, that is possible. We thought so. The starting point was what was published with DQN, and we thought that was a good place to start. Yes. So that's what came out of this first round of experiments. And we wondered how, yes, Alex?
Is there something about Seaquest in particular in comparison to the other games?
Yeah, that's a good question. So is there something about Seaquest that makes it different from the other games? And I don't have a solid answer. I have like a few things that maybe I can speculate about how Seaquest works, but I don't have a solid answer.
Zach, sorry, follow up.
Yep.
Last question. So is it just that for Seaquest, everything was doing kind of badly, and the DQN with 10 million didn't? Like, it looks like those are maybe statistically non-separable. So is it just that everything was doing bad?
Yeah, it could be that. Like these, we can't really compare them. So their errors overlap. Yeah, and there's quite a lot of variance just with the 10 runs. Like we could do more runs. Maybe that would help separate out some of the differences in performance. Yes?
So I would like to know, how do you do search control in Dyna?
How?
Search control. How do you select the starting states and match?
So the states are selected from a planning buffer that has that's size 10,000. So we keep the most recent 10,000 states, and the start states are selected uniformly random from that buffer. And the actions are selected according to the current policy. Does that make sense?
So it's a little bit like the on-policy planning.
Yeah. We can talk, if you have more questions about like the details of how this was actually implemented, we can talk after. I need to get through my, a bit more of my story. So how can we make performance better? So since we're loading start states for planning from the agent's recent real experience from that planning buffer that we keep around, and only rolling out one step, maybe the experience generated by the model is always really similar to what has already been seen anyway. And it's not providing much additional benefit. Maybe. So we can try rolling out more than one step from the start state. So when we load a state, we roll out multiple steps with the current policy. This might generate more diverse experience. So it's pretty straightforward to modify Dyna-DQN. So instead of rolling out a single step, we roll out k steps from the selected start state. And that gives us a planning shape. So we can do, for one planning period, we can do n iterations of k steps. So we would load n states, and from each of those states, roll out k steps with the current policy. So then that allows us to vary this planning shape. So we could do 100 rollouts of one step, 10 rollouts of 10 steps, or one rollout of 100 steps. And each of those requires the same amount of computation from the model. So this is what the results look like. So the experimental setup is the same as before, except now we are varying planning shape along the bottom here. And the baselines are the same as before. So this is DQN 100K, this is DQN extra updates, and this is DQN 10 million.
Sorry, are you doing K one-step backups, or are you doing one K-step backup? Like the actual Q-learning backup that you do?
Yeah, it's done in the same way that DQN. So we roll out, let's say 100 steps.
The rollout is to generate the
yeah, and then those get placed into the experience replay buffer, and
you're still doing one-step backup.
yeah, exactly. Yeah, and then those those training steps can happen during the rollout. So so in a 100-step rollout, you do 10 steps of the rollout, and then you do select the batch for training, update your value function, and then continue. So we can see that the performance of Rollout-Dyna-DON increases as the rollout length increases. Yes, Rich?
Can you just remind me which number is first?
So this is the number of iterations of planning. So this is 100. You load 100 states and then do one step from those 100 states. And this is load one state and do 100 steps. So in general, performance increases as you increase the rollout length. And kind of interestingly, Rollout-Dyna-DON outperforms DQN 10 million in Seaquest, BeamRider, and Space Invaders. So the DQN 10 million baseline is here, and it's way above in Seaquest. It's above in BeamRider and Space Invaders. So what's up with that? We don't have a good answer. Haven't been able to figure out why this happens, but we kind of have a hypothesis. So Rollout-Dyna-DON induces a different training distribution than DQN. So model rollouts use the current policy, but start states are drawn from past experience, distributed according to the behavior of an older policy. So
I'm sorry, Zach.
yeah.
What are you trying to explain?
Why? So how can Seaquest with the same number of updates, outperform DQN, like the same number of updates to the value function.
Okay.
Right.
So if you're doing even better than the
Yeah, because they're seeing the same amount of experience, of new experience, and they're doing the same amount of updates.
Now, the rightmost thing, 1 by 100, is only getting one simulated experience. It's 100 length long.
Yeah.
And then sticking it in the to be replayed.
Yeah.
So it's really getting many fewer updates.
So it's getting the same number because we count. So every 4 steps we do an update, and every 4 steps of real experience or experience in the model. So in a 100-step rollout, we're going to do 25 updates because every 4 steps we draw a batch from the experience replay buffer and then update the value function.
So it's just a search control issue.
Yeah.
I see. Just where you're starting.
Where you're starting and what the shape looks like.
But it's still doing only 1 every 4 simulated model-based time steps.
Yeah, that's doing update every 4.
Requires benchmark is getting 100 extra. It's getting all 10 million time steps of experience. So it's fewer updates.
No, the same number of updates. So the Rollout-Dyna-DON runs get the same number of updates as the DQN 10 million. Maybe it's not clear. We can talk after.
Can you use the same policy for the rollout as for the real experience?
Yes. Okay, what was I saying about this? All right, so Rollout-Dyna-DON is seeing a different training distribution than regular DQN, and it could be that this change to the training distribution caused DQN to find a good policy more quickly in some games. And in some preliminary experiments, we tried decreasing the size of that planning buffer. So the states that are sampled to start planning will look more like what the on-policy distribution, the current on-policy distribution of states looks like, and maybe that'll make Rollout-Dyna-DON look more like DQN. And so if you do that, it tends to make the performance of Rollout-Dyna-DON decrease. But that's kind of preliminary. I don't have anything really concrete to say about that. But
I think
yes.
you asked this earlier, but is when you do your 100-step rollout, and you say you update every 4 steps, do you use the most recent policy, or do you do the 100-step rollout first with the older policy? If you see what I'm saying. You're going to do a 100-step rollout on policy.
Yeah.
And you were saying that you update along the way as you're doing the rollout.
So you're using your most recent policy. So your policy can be changing during that rollout. So you might do 4 steps, do an update, and that changes your policy, and then So we don't fix the policy, then do a rollout. We allow the policy to change during the rollout. All right. So how am I doing for time? OK. I'll try to get through this really quick. So that was with a perfect model, so second copy of the emulator. So can we do it with an imperfect model? So a model that was learned from experience. So to do this, we extended O et al.'s action conditional prediction model. So now instead of just predicting the next frame, we predict the next reward as well. So the details aren't really that important right now, other than we trained 3 for each game. We trained 3 instances of this model on a different training data set. And so the models are the result of a single training run. So we don't want to compare the effectiveness of the training procedure between the models, but we just want to evaluate the impact of model error on Rollout-Dyna-DON. So this is what the results look like. So as with the perfect model, there's a rollout length that's greater than 1 that outperforms 100 by 1 planning. So like the best performer here for Seaquest is at 10 by 10. So it's interesting to observe that there's a tension between the benefits of doing long rollouts and that the model's errors compound to make long rollout predictions unreliable. So this results in the best performance at an intermediate rollout length. And this is most evident, it's easy to see it in Seaquest. Performance tends to increase, but then tends to decrease as the rollouts get too long. So that's kind of a limitation of the learn model. It can't roll out forever. So to our knowledge, this is the first time that a learned dynamics model has been used for planning in this particular way in the ALE. And planning shape seems to be critical for extracting the most benefit from the model. Rollout lengths greater than 1 outperform 100 by 1 planning and DQN extra updates. So this might be an effective strategy for generating novel experience. So the most obvious next step is, can we learn the model online while we're doing planning? So Rich said in his talk last Monday that sometimes the big problem is hard to tackle head on and we need to assemble the pieces. So this work doesn't go all the way, but it's an incremental step which hopefully gives us some insight into how these things work. And there are also some other potential ways to use the model. So Pan et al. And Goyle et al. Use inverse dynamics models, like prioritized sweeping. And then maybe we can combine forward models' ability to reveal novel states and then backwards model ability to efficiently improve the value function to create some kind of super algorithm. All right, any questions? Yes?
So think about the interesting result further back where you are doing longer rollouts, and they get the same experience for Rollout-Dyna and the Dyna that gets 10 million samples from an environment. Could it be somehow that seeing an alternative trajectory from the same place is somehow helping you average across different things you could have seen, and that's just a better way to use samples? Yeah,
I think that's one of the, so the point was maybe that revisiting old states and then doing something different in that state is just a better way to use samples, and I think that is your
that's what you said. Okay. I didn't get what you're saying.
Yeah, no, that was your point.
Yeah.
Right. Yes, and and I agree. I think that's a really good hypothesis. I just don't know how to test that to tease it apart from other things that might be going on in there. I like that explanation. I think it makes sense, but I don't have any evidence to show that that's other than the performance to show that why that might be true. Yes.
What was your epsilon, and what do you think would happen if you used a different epsilon?
Yeah. So we used an epsilon greedy behavior policy, and we annealed epsilon from 1 to 0.01 over the first 10% of the frames during training. So in the 10 million case, that was over the first million frames. And in the Dyna DQN case, that was over the first 10 million combined model and emulator frames. I'm not sure what would happen if you changed epsilon. There's a few preliminary things that I've done playing with it, and it doesn't seem to have a very big impact on what the ultimate performance is. But I don't have anything stronger to say about what would happen if you tweak epsilon. Yes?
This is really interesting to see. Can I just ask again about the perfect model?
Yeah.
So the policy's the same. The model is identical to reality. So the only thing which is different from actually the original DQN is the fact that instead of, the distribution in the limit, the distribution of states is exactly the same.
Yeah.
And it should get exactly the same result. So the only difference is whether you run complete trajectories all the way from the beginning, and then run another complete trajectory, and then run another complete trajectory. That's what DQN is doing.
Yeah.
Or whether you run a trajectory, and then from a certain point partway through that trajectory, you branch off and kind of go to the k steps.
Yeah, do a piece of it, yeah.
So it seems like these results are somehow suggesting that you want to get just the right trade-off between like, the diversity of those states that you're seeing, that if you were to reset into a completely different trajectory, all of the states along a trajectory are very correlated.
Yeah.
So you don't get maximum diversity by running complete episodes, nor do you get maximum diversity by setting k equal to 1, because you're only going one step away from each point of your trajectory.
Yeah.
If you use something intermediate, then you kind of maybe get the best of both worlds. You kind of get something which is taking you quite far away from your existing trajectory, but it isn't as expensive to generate a new state that's really different from what you've seen as running a completely different trajectory.
Yeah.
I don't know. Am I barking up the right tree here? Is this?
Yeah. Yeah. No. I think that's a good explanation, and that's I think what my intuition is about what's going on. Like it seems. Yeah. Like I agree with what you're saying. Yes, Nico.
So
Or.
just to follow up on that explanation makes sense to me if you look at the learned model shapes, but if you look at the perfect model, the best thing to do is to take the longest trajectory that you can.
Yeah.
Within your budget, and so do you think that if you have maybe more than 100, like much greater than 100, you will see a similar curve shape, like you sort of mentioned? Or,
Yeah. So I've done some preliminary stuff where that if during planning you do as long of a rollout as you can. So let's say finish the episode. So that actually your performance will starts to come down as you start doing longer and longer episodes. And if you always load the start state and do full episodes of planning, then it looks really similar to just doing regular DQN. Roshan?
So you talked a little bit about the planning buffer, like whether it was small. So what is the size of the planning buffer relative to the experience replay buffer for DQN? The reason I'll tell you why I'm asking this, because if your planning buffer is really small, then you're doing your rollouts based on states that are very similar to your current state.
Yeah.
So they're in the recent past.
Mm-hmm.
And so you can imagine that doing lots of updates from states that are similar to your state right before you act in that state is good, right? Like because you're making lots of updates to your value functions and such that are like good for your current state.
Yeah.
And that's kind of rolling along as you go further and further. Whereas your experience replay buffer has a bunch of states from way back in the past, and making updates from random states drawn from there is not as localized on your current performance, right? So it seems like you could almost have a model that's good for the state you are in, and that keeps being good for the state you're in if your planning buffer is small enough. Right? So that's possibly another effect. That,
Yeah. So making the planning buffer smaller, like you said, makes the states that you start planning from more similar to what you're experiencing under your current policy. But that tends to decrease performance. And I think maybe, and having, so let's say you always load like the previous state to do planning, like a planning buffer size of 1. So that doesn't do as well as keeping around more states. So like we used a planning buffer size of 10,000. And so keeping around, so allowing start states to be chosen from further back in history seems to help more than just choosing the most recent state, for example.
Is there a trade-off? Is there a point where it switches? Like you can imagine that too short is bad, and then there's some migration along there. Too much is bad as well.
Right. I haven't tried that out. We just have kind of used a fixed size. So I haven't tried bigger. I haven't tried greater than 10,000. But you could imagine selecting start states from your entire experience replay buffer, which I haven't done. All right. Yes.
It just reminds me of the dynamic difference between value iteration and policy iteration. Usually policy iteration are more effective. So I'm not sure exactly how these match, but in this case, probably some very slowly, maybe get kind of similar to the video there. It's more like a synchronous, each iteration is more like a synchronous queuing iteration, as I understand. But in that case, if you do queue-learning and you actually pick what the state action pairs that your current, say, greedy policy would visit, and in that case, the queue-learning would come much faster than when you just select uniformly randomly state action pair. I reminds me of just somehow resembles the performance you observe. I know there could be still very many differences in the algorithm settings here.
Yeah. Okay. Yeah, that's interesting. Maybe we should talk more later. I think that the Q-learning stuff I'm not super familiar with. So. All right.
Okay.
Yeah.
Last question.
And what are model A, B, and C? Are those learned? If they're learned, how are they different? If they're not learned, are they some perturbation of the perfect? Well, I just missed what you said. So to me, I have no idea.
Okay. So the learned models are.
How are they different?
Okay. So they're neural network, and the architecture is the same in each case, but they're only different from their training data and the kind of the training schedule that they were given. So the way that they represented the training data.
So why that one case, there was one, we flip back to the pictures. It looks like the orange guy, I don't know what's special about him, but he seems to do a bit better, at least in certain of these games, and I just was curious what's.
Yeah. So like Model C does really well in Pac-Man, but it doesn't do so well in Seaquest.
Is there anything you say about that? Or?
Not in 10 words or less. Okay. If you want to know more about it, you can come talk after. So.
Okay, thank you, Zach.
Right.